In this video, we will talk about extrema of real-valued functions. This slide and the next is a summary of all the main points of this video. We will discuss critical points and the extrema. We'll talk about absolute maximum and minimum and how to find them in general and also on a compact set. Once we've gone through these two overview slides, there'll be another 2 or 3 problems, and then there's 2 problems for review for you to try. We will start with our definition. So if we have a function f from Rn to R, so it produces a scalar, then a point x0 in Rn is called a local minimum of f if there exists a neighborhood v of x0 such that for all points x and v, f of x is greater than or equal to f of x0. So it's what we think of the minimum. Everything else plugged into f gives you something greater. Similarly, it's a maximum if all the other points plugged into f is less than f of x0. And the point is called a local extrema if it's either a local min or local max. And it's called a critical point of f if the derivative of f evaluated at x0 is equal to 0. And a critical point that is not a local extrema is called a saddle point, kind of what an inflection point was in one variable calculus. We have the theorem. So if we have our function f and it's differentiable and x0 is an Rn and x0 is a local extrema, then we have the derivative, the partial derivative matrix evaluated x0 is equal to 0. That is, if x0 is a critical point, then the gradient of f evaluated at x0 is equal to 0. So we'll do an example. We'll find the max and min of the functions, 2 functions. F of x is equal to 2x plus y squared. That's one problem. And the second problem is to find the max and min of g of xy is equal to x squared minus y squared. So we'll start with f, the function f. So the gradient of f, partial derivative with respect to x, that's these first order derivatives, is 2x, 2y. We set that equal to 0 because that's how we find critical points. So if it's equal to 0, then what we get is that x and y must be equal to 0. Since f of xy, so this x squared plus y squared is greater than 0, then 0, 0 must be a minimum. Our second problem, we look at g of x, and we take the partial derivatives, or the gradient. It's 2x, and minus 2y is equal to 0. So that also gives us 0, 0, but this is a little bit different. But this is different because if we look at g of x0, so let's consider the point 1, 1, where x is equal to 1, y is equal to 1. If we plug in 1 here, we see that g of x0 is greater than g of 0, 0. But if we plug in 1 here, we get a negative number, so g of 0y is less than 0, 0. So different sides of this of the xy line is going to give you, in some places things are greater than 0, 0, in other places they're less than 0, 0. So 0, 0 is a saddle point of g. So to determine if a critical point is a min or maximum, we can look at the graph and analyze it, but we also have a second derivative test, just much like in one variable calculus. And to that end, we will reintroduce the Hessian matrix. If we recall when we talked about Taylor polynomials, the Hessian matrix is the matrix of second order partial derivatives. So I kind of wrote it here. And there's this theorem that says suppose we have our function r into r, it has second order partial derivatives at point x0, then the Hessian of f at x0, and we denote that this way, the Hessian of f of x0, is the quadratic function defined by, so here's the definition, 1/2 on the sum of the Hessian matrix evaluated at h0, hi, hj, where h1, h2 is equal to x minus x0, y minus y0. So the x0, y0 is in Taylor series, that's what we were expanding around. Here, that's the point we're looking at as a possible critical point. So another way of writing this formula in matrix form is h of f of x0, h is 1/2, our h1, h2, again that's just our x minus x0, y minus y0, our Hessian matrix, our matrix of second order partial derivatives times our Hessian matrix again. We have this lemma that lets us classify equations of this form. And before I go into this lemma, I do want to point out that here in our matrices of partial derivatives, our d2f dy dx is equal to d2f dx dy. If you recall, when you take the second order partial derivative and they're mixed, in other words, there's a dx dy or dy dx, they end up being equal. So this is the b term. Anyway, so this form is called positive definite if and only if a, that's the first term in the upper left-hand corner, is greater than 0, and the determinant of this matrix, which is equal to a times c minus b squared, remember these two are equal, is greater than 0. Similarly, h is considered negative if and only if a is less than 0. This upper left-hand corner element is negative, and the determinant of b still needs to be equal to 0. We are going to use this now in our second derivative test. Here I have it written. So if we have our function, Rn is a critical, x naught is a critical point of f, the Hessian matrix, if it's positive definite, then x naught is a relative minimum. It's sort of like in first order calculus, if the second derivative was positive, that means it was concave up and you had a minimum. So same thing. If it's positive definite, then x is a minimum. Similarly, if our Hessian function evaluated at f of x naught is negative definite, then x naught is a relative minimum. So next I have this example over here. If we have the function f of xy is x squared plus y squared, and g of xy is equal to x squared minus y squared, these two over here, we can calculate the second order partial derivatives. So looking over here, my gradient of f is 2x, 2y. So the derivative of this with respect to x is 2. Derivative of this with respect to y is 0. Similarly, derivative of 2y with respect to x, is 0, and the derivative of this with respect to y is 2. And then we can put in our 1/2, our x, and in this case, we're considering 0, 0, our critical point. So this is x minus 0, y minus 0, times x minus 0, y minus 0. So now I can look at that, and I can see that this over here, the a term is greater than 0. If I look at the determinant, it's positive, in which case that means I have a minimum. For our second problem, g, I can get our Hessian by looking at my gradient of g. We start off with 2x, derivative with respect to x is 2, derivative with respect to y is 0, and then we look at negative 2y, derivative with respect to x is 0, with respect to y is negative 2. And now when I look at the first entry, 2, that is greater than 0, but I look at the determinant and that's going to be negative. And so the negative determinant, and I didn't list this because I guess it doesn't go in the lemma, but it doesn't go quite in the theorem either. But because of the negative determinant, we say that this has a saddle. So the negative determinant is indicative of a saddle. Next, we'll move on to absolute maxima and absolute minima of a point. So it's an absolute maxima if f of x is, or f of x naught is greater than all the other x's in some set A. And it's a minimum if it is f of x naught is less than all the other f of x's. Next we have the idea of a bounded set. So set D in Rn is bounded if there's a number m such that the magnitude of all of our x's are less than m. So there's an upper bound on x. And the set is closed if it contains its boundary points. So a set is called compact if it is both closed and bounded. We'll do some examples, and it kind of is something that you would intuitively think of as bounded. And these definitions are important because we have this theorem, the Extreme Value Theorem, or also called the Max and Min Theorem. So if D is compact, so it's both closed and bounded in Rn, and a function f is continuous from D to R, then f assumes its max and minimum values at some point x naught and x1 of D. That is, there are points x max and x min in D. What this means for you is if your domain is closed, in other words, you're not looking over the whole xy plane, you're looking at just some portion, a specific closed portion with a boundary, and you know that the space is also bounded, then you know that you have to find a max and a minimum. There are times when you take the gradient, you set it equal to 0, that you will miss points. I will show you an example of that. And generally what you do if you're missing points is you look on the boundary, and you will see that example soon. So what this theorem tells you though is you'll definitely be able to find a max and a minimum. And we have this other theorem that says let D be described as in the previous theorem. It's compact. F is continuous. It's of class C1. If F assumes its max or min value point at x naught, then x naught will be a critical point of F. And we'll continue on with this little algorithm on how to find the min or max. You want to locate all the critical points of F. And then you want to find the critical points of F when you view it as a function only on the boundary. So I'll show you an example. But basically you're going to look on the boundary for critical points. Then you're going to compute all the values of F at these critical points, and then you're going to compare the values and select the largest and smallest. And here is our example. Find the min and max values of the function f of xy is equal to x squared plus y squared minus x minus y plus 1 in the disk formed by x squared plus y squared less than or equal to 1. So here the domain, we're subject to this disk, and you can see it's definitely got a boundary at 1, and it's has a max and min, so it's bounded. And from this theorem here, we're going to be able to find both a min and a max. To start by finding all the critical points, we're going to take the gradient and we set it equal to 0. I could have put another 0. But now we have 2x1 minus 1 is equal to 0, and 2y minus 1 is equal to 0, which gives us x and y is equal to 1/2. Now we're ready to look at the boundary. We're going to find the critical points of f viewed as a function only on the boundary. So the boundary can be parameterized by sigma of t is equal to sine t cosine t, because again it's the circle of radius 1, and t is going to go from 0 to 2 pi. So now we can evaluate f sigma of t. We have our function composition. So our sigma of t, our sine t is going to be x, our cosine t is going to be y, and we're going to plug it into our function. So we have x squared, which is sine squared, plus y squared, which is cosine squared, minus x sine minus y, which is cosine, plus 1. And we can do some simplification, and this is 2 minus sine t minus cosine t. To locate the min and max, so we can find the critical points along the boundary, we take the derivative and set it equal to 0. So taking this derivative, our 2 goes away, we have minus cosine t plus sine t equals 0, meaning sine t equals cosine t, and that happens at theta equals pi over 4 and at 5 pi over 4. Now we have our critical point over here at 1/2 that we got by setting the gradient of f equal to 0. And then we have these two other critical points that we got by looking at the boundary. So f of 1/2 is equal to 1/2. F of sigma of pi over 4 is square root of 2 over square root of 2, f of square root of 2, f of this, which is equal to 2 minus square root of 2. F of sigma of 5 pi over 4 is f of this, which is equal to 2 plus square root of 2. And then we have f of 0, which is f of 2 pi, which is f of 0, 1. And the reason why we plugged in 0 and 2 pi is because those are our endpoints, and we didn't consider those. And so comparing all these values, we see there's a minimum at 1/2, and there's a max at negative 2 square root of 2, comma, negative square root of 2 over 2. So the moral of the story is you use your gradient to find critical points, and if you're on a boundary, a compact domain, you're going to also look at the boundaries to find critical points. And even the boundary might have endpoints that you want to consider, endpoints or vertices. Here's another example where we're trying to minimize a distance. So we have the function, and the instruction says to graph the function. I'm not going to do that. But graph the function of g of x, y is equal to 1 over xy. It's a surface in R3. Find the points on the surface that are closest to the origin. As I mentioned, you are minimizing the distance function. So I have the distance function here. And for this equation, we have x squared plus y squared, and we substitute in 1 over xy for z squared. And we also want to note that this distance formula is minimized when what's inside the square root is minimized. So we can just work with what's inside the square root just for easier computation. This trick, when you're trying to minimize distance, that you basically minimize what's inside, is one of those things you want to know when you're taking an exam so you don't have all these messy extra computations. So to find the critical points, we're going to take the gradient. And so here I have the gradient, the derivative with respect to x, derivative with respect to y, and I set it equal to 0, 0. Here, multiplying everything by x cubed y squared, that's going to give me 2x to the fourth y squared minus 2 is equal to 0. Similarly, multiplying everything by x squared y cubed, I'm going to get 2y to the fourth y x squared minus 2 equals 0. And what that gives me is y squared is equal to 1 over x to the fourth. And then plugging it in, doing some algebra, I'll get 1 over x to the sixth is equal to 1, which implies x is equal to plus or minus 1, and y is equal to plus or minus 1. It will give us these 4 critical points. So now I'm ready to look at the determinant. So I look at my gradient. No, where is my gradient? Here's my gradient. Take derivative with respect to x. Take the derivative with respect to y. Over here, I look at my y term in my gradient. Take the derivative with respect to x. Take the derivative with respect to y. What I see is this first term here, the a term, that's going to be positive because I have my x to the fourth and my y squared. So all of this is positive. And then when I do my determinant, well, this is positive. And then actually, I don't even have to do all of this because I can just plug in my 0.00 at the origin. And I can see I get 2. This term is problematic for 0, 0. But you can actually do the math because it's actually not too bad, because this is x to the third. Anyway, you can do the math and you'll see that this determinant is greater than 0. So what that means is all of our points are, the determinant's equal to 3, so all the points are minima. I threw the definition of strict local minimum and maximum in here because some textbooks cover it, but I'm not really going to talk about it. But I will say that critical points for which d is not equal to 0, the derivative is not equal to 0, are called non-degenerate critical points. And such points can be minimum, maxima, or saddle points. So here's the first of our very important examples. So if we have t, and this in one of the books is described as a temperature function on a plate, a two-dimensional plate, is equal to x squared minus xy plus y squared plus 1, where the domain is closed and it's a square as described here. So y is equal to 2, y is equal to -1, x is equal to -1 to 2, and it includes the borders. I can take the derivative of t with respect to x, and so I get my 2x minus y equals 0. Derivative of t with respect to y, so I get minus x plus 2y, and I set that equal to 0 to find my critical points. I multiply this by 2 and then add everything together, and I get, I multiplied this by 2 and I added everything together, and I get minus 3x is equal to 0, which means x is equal to 0, which implies that y is equal to 0, which is in the square. Since you're looking on a limited domain, you do actually want to verify that it's in your domain that you're looking at. So now I can do my Hessian. So I look at my derivative with respect to x, and I take the derivative with respect to x again and get 2. With respect to y, I get -1. I look at my derivative with respect to y, and I take it with respect to x again, I get -1. With respect to y, I get 2. So you can see that this term is positive. You can see the determinant is going to be 4 minus 1, so it's also greater than 0. So it's a positive definite, which means that 0, 0 is a minimum. If you recall, because it's a bounded domain, you want to look at the boundaries so that you get all of the max and mins. So we're going to look at the edges of y equals 1, and x goes from, y is equal to -1, and x goes from -1 to 2. So that's going to give us f1 of x, and I'm going to plug in t of x, y is equal to -1, which will give us x squared, and then y is equal to -1 plus x, and then -1 squared is 1 plus 1 is 2. So this is my f of 1 of x, where y is equal to -1. I set the derivative, which is 2x plus 1 equal to 0, and I get x is equal to -1/2. And then I can plug back in, I already know my y, so I'm going to check x is equal to -1/2, y is equal to 1. In addition, I'm going to check these vertices here, because that's kind of the the edges of my y equals -1 boundary. So I'm going to check the 1, 1 vertice and the 2, -1 vertice. Sort of like before when we had the sines and cosine and we checked the 0 and the 2 pi. We're checking, not only are we checking the boundaries, but we're checking the vertices or the very endpoints of the boundaries. Now we're going to look at the edge y equals 2 and we plug it into f of x and we get, so we have x and 2 and we get x squared minus 2x plus 5. Take the derivative, set it equal to 0, we get x equals to 1. So now we need to check 1, 2, as well as these upper vertices, which is -1, 2, and 2, 2. Next, we're going to look at the x equals -1 line. And so we're going to plug that in, and we're going to get f3, x minus 1, y. So we plug that into here, and we're going to get 2 plus y squared. We take the derivative, set it equal to 0, we get y equals -1/2. So we also need to check -1 1/2. And then last we have x equals 2, this line here, we plug it into x equals 2 into here, we get f4, which is 5 minus 2y plus y squared. Take the derivative, set it equal to 0, we get y equals 1. So the other point we need to check is 2, 1. So we have all these points, 0, 0, and I underline them all in blue, 0, 0, -1/2, 1, -1, 1, 2, -1, 1, 2, -1, 2, 2, 2, -1, 1/2, and 2, 1. And we plug in all the points to find the smallest, which is going to be 0, 0. We plug it into f, and we plug in, and then we'll find the largest is at 2, -1, and also, which is equal to -1, 2. So this square actually had a lot of calculations. So those are our main points about max, min, saddle points, how to find them by setting the gradient equal to 0, how to determine if it's min or max by looking at the Hessian, the second derivative matrix, and then also trying to find the max and minimum, the absolute max and minimum on a compact set involves looking at these boundaries. By way of review, I have 2 problems for you to try. These 2 problems here, so you can pause the video, give them a try, and then come back and I'll have solutions for you. Here are the solutions. And that's it for this video. Thank you for watching.